Yeah, very good.
Let's see that.
All right. Welcome everyone. Thank you for joining us today. We have three wonderful guests for us. Professor Dongyan Chu, he's a kind of somewhat multi-year friend of mine. Professor Antonio Bianchi has actually been on this campus in 2019, gave a wonderful talk. And Professor Berkay Celik has actually worked with one of our Rose students in the past. So they all have connections to Rose Home. So with that, take it away.
Well, thank you so much, Zach. So it's always great to get together, and so it's my great pleasure to be here. It's my very first time on the Rose campus. I'm very impressed by the very quiet and very well facilitated campus here. I was just talking to my colleagues that anytime at Purdue on the campus, you actually see students walking very crowded. So I actually like this a lot. So we would like to have so today I would like to make our kind of a presentation a bit kind of casual and informal. We would like to just have a kind of an informal showcasing of some of the research development effort in the broad area of cybersecurity and cyber physical security that are going on at Purdue. And so I've been talking to Zach, for many years that we should, we should collaborate and do some work together. So I'm hoping that our visit can actually be a very concrete start of that process. And also we will very much love to involve many of you in our joint research development effort. So I think this is a quick kind of a description of why we are here today. And so I guess I don't have to introduce you guys. So so myself, Antonio, Berkay, so we are 3 of the 4 faculty members at Purdue University's Computer System Security Lab. So in our lab, we have 4 professors, myself, Berkay, Antonio, and also Professor Dave Tian, who is not able to join us today. And so the 4 of us actually run a kind of a large computer systems or cybersecurity research lab, with more than 25 graduate students. Most of them are PhD students, and our lab was founded back in 2019, right before the pandemic. And we would like to actually, cover a wide range of topics in cybersecurity, all the way from the lower level hardware, microelectronics, going all the way up to software, firmware, system software, application, network, and also the interaction between cyber systems with the physical world, such as industrial control, manufacturing, smart vehicles, et cetera, et cetera. So so this is actually a kind of a quick overview, like a fact sheet of our lab with 4 faculty, 25 PhD students, and many master and undergraduate students. So we do have our dedicated lab space on campus, and we also have a wide range of cyber and physical experimentation infrastructure, such as the computers, smart devices, as well as physical things like cars, drones, manufacturing machinery, things like that. So we do have some real physical things that folks can play with and do experiment. So we promote student and scientific advancement through the investigation of emerging technologies, right? Where you see the fusion of computing, communication, AI, and physical autonomy and system. So this is I think this is a photo that was taken earlier this year, right? During our picnic.
2 weeks ago.
2 weeks ago, yeah. So when it's still warm outside, so we did get the opportunity to.
The last day.
Yeah.
The last warm day.
Yeah. So. Yeah, that's right. Then it started to get chilly. So a little bit about the Purdue cybersecurity ecosystem. So Purdue is actually one of the, I promise that this will be one of the very few slides that I brag about us. So Purdue is, so cybersecurity is an area of traditional strength at Purdue University for many decades. So this year, the U.S. News ranked the cybersecurity undergraduate program at Purdue as number 6, up 1 spot from number 7 last year. And more academically, there is another ranking called CS ranking, where they look at faculty and student publication at top venues in each sub-area under computer science. And in the sub-area of computer security, Purdue has been ranked number one nationwide for, I think, 3 or 4 years in a row. So this actually shows the quantity as well as the quality of the research work and the productivity of faculty and students. So we have a large kind of an industry government kind of a presence in the ecosystem. So we involve we are supported by and advised by and collaborate with government, national labs and companies in a variety of cybersecurity research topics. So these are also the partners where we send our students, undergrad, graduate, master, PhD student for both internship and full-time employment. And we also have a kind of a Cyber Plus X vision where we actually force our cyber students typically from CS, ECE, computer technology, to work with engineering students, like students in mechanical, aerospace, industrial, chemical engineering, so that they can look at the cybersecurity research challenges that exist in those application domains, not just the traditional, what I call cyber, but we want to focus more on cyber physical, right? The security threats and vulnerabilities that exist in, let's say, your traditional cars, EVs, manufacturing systems, our nation's supply chain and critical infrastructure. So these are some of the industry partners that heavily recruit our graduates, both undergrad and graduate, at both graduate and undergraduate levels. So we actually host career fairs just for these partners. So basically they have, for example, specific technical interests as well as, constraints such as citizenship and things like that. We're actually accommodating a lot of these, very national security and defense-oriented kind of a consortium. So I guess this is just a kind of a quick animation of, like very sophisticated cyber attacks and cyber threat that you see nowadays. So it's not only, increasingly you see the threat coming from the cyberspace, propagating into the physical domain, right? So the attack, as well as especially their impacts, are no longer constrained or contained within the computer. So your computer gets hacked, or your cell phone, like data gets stolen. So that is still, very serious consequences of cyber attack. But increasingly, you see that the consequences of cyber attack start to manifest themselves in the physical domain. For example, the attack against the Colonial Pipeline, fuel supply chain will actually affect the price of gas, right? And also the attack against, a ransomware attack against the Subaru plant right outside Lafayette will actually halt their car production for a whole week. Things that are in the more and more in the physical domain. So we are actually interested, and also attacks against, you can imagine, the power supply, water treatment, you name it. So we are interested in looking at the interplay between the cyber actor as well as the physical components, and look at especially the interplay and the dependency between them, and identify opportunity to address cybersecurity threats and vulnerabilities both proactively and reactively, right, in a very holistic fashion. So that's why we, on a regular basis, involve students not only in computing, but also in science and engineering areas, right, to work on problems together. And just as another quick example, this is actually a advanced persistent threat attack forensic report that is generated by the state-of-the-art cyber forensic agent. So this is actually automatically generated without any human involvement. So it doesn't read very well, right? So you see the red words as the verb in a sentence, but these sentences, they're not easy to parse. So this is today, right? So what we are going to do, and you can also get the visual representation of the same attack report. But this is what we really want to happen, maybe 3 years, 5 years down the road. So we want agents, powered by AI, to work seamlessly with the, hey, how come it goes so fast? Anyway, so we want to have human investigators working side by side with the AI-powered software agents that has the knowledge about general cybersecurity as well as the specific system and infrastructures that they are protecting, working together with the human investigators, detecting suspicious activity, identifying the specific vulnerability that might trigger this attack, and also suggest responses in a cost-effective fashion. So we want this to be done jointly by AI and human. So basically, human is always in the loop, but we want to, our slogan is that we should outwit, outscale, and outspeed the adversary, because cyber attacks happen at like increasing speed. Things can be compromised within seconds. So on the defense side, we need to catch up, right? We need to catch up in terms of the scale, in terms of the speed, and in terms of the intelligence. And this is another example of agent, but this time the agent operates in the physical space, where the agent look at the control decision made by the traditional controller of a drone, right? So this is actually a kind of what I call a flight school, right? Using a simulator. So you kind of give the agent all kinds of adversarial condition somehow to, so that the agent can actually figure out what is the best way to respond to a adversarial kind of operating condition. And based on that, we hope the agent will actually learn about, how to respond to, anomalous scenario. And then in the real flight, we let this agent to run side by side with the classic controller, like a PID or, controller. And somehow this video doesn't play, but it should. Anyway, so if this plays, I'm going to send Zach a link to the PowerPoint, and then you can actually watch the video. So you will see that the drone now actually fly in the presence of cyber attack. And even if the controller, the PID, has no idea how to stabilize the vehicle, that agent, after the training, is able to tell the controller, hey, reconfigure your control parameter this way, you will be able to stay stable, even in the presence of these unseen or new cyber attack. So Antonio, maybe I will invite you to talk about some of the more hacking-oriented stuff.
Yeah, so I'm one of the other professors in our research group, and so I will just present very briefly 4 or 5 different projects we have been working on, and of course to every one of these projects, connected to each one of these projects, there are papers and publications that you can check maybe in the website that we link at the beginning. But so this is like an area we have been exploring, sponsored by DARPA, in which the general idea is kind of intuitive. The idea is that we have millions of devices right now that are that contains vulnerable software, and it's vulnerable because it's unmaintained. So maybe the code actually is well known that contains vulnerabilities or contains security issues or contains some bug, but it's very hard to maintain. No one cares about maintaining it. And here I'm showing you 4 examples. One is engine. So some engines actually are controlled by millions of lines of code, industrial controller, IoT devices or home routers, and even spacecrafts. So these are all cases in which they run code. The code has maybe been written 30 years ago, 40 years ago, I guess, for some spacecrafts, and no one is interested in maintaining it, or maybe someone is interested in maintaining it and updating it, but it's extremely hard to maintain. For instance, I talked with one company actually developing one of these engines, and they told us, yes, we still have the source code of it, but the only way to compile it is on some Windows 95 machine that we need to run it now in the virtual machines, and it's really hard, right? So, the goal of this project is how to patch legacy code and how to do it reliably. And so, to do this, as part of this effort, we have developed a binary patching tool that allows you to specify how you want to modify an existing binary. And when I say binary, I mean compiled code. How you want to modify a piece of compiled code without having the original source code and without recompile the entire code. And so this tool allows you to specify how to do a patch at a different level of granularity in different ways. And then on the other end, you also want to verify that the generated binary it doesn't break anything, right? Because another reason why people really don't want to patch sometimes is that they're afraid that the patch is going to break something, and this unfortunately happens. I think a good amount of spacecraft actually got lost just because some software update broke something, and then no one could go to Mars doing a rollback of the software update, and so the spacecraft was lost. And so we developed a tool to kind of compare the original binary and the patch binary and trying to show in a readable way the differences so that the developer can be sure that the only differences present in the code in the patch binary are the ones intended by the patch. And in this way, allow, hopefully in the future, more and more devices being updated and deploy countermeasures for vulnerabilities that are found very often in the software running in these devices. For instance, I don't know, a lot of IoT devices, they run the Linux kernel. The Linux kernel, maybe every few months some new vulnerability is found, but is not that often updated in these IoT devices. And so just some results, we were able to patch and verify the software running in I guess it was that real world engine. And also we can create patches at the binary level for multiple embedded systems, and we're able to verify that they do not break the existing code. And this idea of patching also, this patching idea also has been reflected in other research projects. Two of them are related to drones, and I think my colleague will present them later on. So, okay, another kind of research area we have been working on is, now AI is everywhere, and but still we are low level, or we do a lot. We like to do a lot of research on low level things. But one thing that we realize is that a lot of these AI models are used in IoT devices, or what is typically called edge devices, like sensors or cameras, or something like Alexa. And these devices, they run machine learning models that are being compiled into binary software. So again, you have some compiled software, and in this case, the compiled software is pretty special because it implements what is called a deep neural network that is used by as part of the machine learning algorithm. And what is interesting here is that, so of course you take a neural network and then in a high-level representation of a neural network, something that you can define with tools like TensorFlow or other tools, and then there are dedicated compilers that are able to compile that neural network and create executable code that runs the inference part of the network in a way that is typically very efficient and is designed to be run in like low-power devices like IoT devices or network cameras or things like that. For instance, a network camera might use a neural network to recognize when some person moves, or to recognize who is trying to enter in a house or something like that. Okay, so as you might know, one thing that in security is often done is to try to do reverse engineering. That is to getting a binary understanding what it does, no? And maybe, I don't know, maybe some of you have tried to use reverse engineering tools like IDA-Pro or Hydra as part of Capture the Challenge competition. And those tools are great, they are not perfect, but they're typically quite good with normally compiled code. But if you try to open a binary that implements a neural network with those tools, you're gonna get something like this, and something like this repeated for maybe 100 functions like this. So this code is pretty unreadable, and it does a lot of mathematical operations, a lot of loops, and it's basically impossible to understand what's going on here. And this is how the binary is actually implementing, those matrix multiplications or convolution operations that are needed by neural network. But if you try to reverse engineer something like this, you will never really figure out what is really this network do, doing what's the high-level representation of this network. So this is not the right approach. The right approach is to develop a dedicated tool that is able to extract the high-level representation of the network. And this is what we did in our paper called D&D. And so we developed a tool. It's actually open source that takes a binary implementing neural network, is able to extract its high-level representation, including all the weights, all the connections between the nodes, all the hyperparameters. And so this was kind of the first step of this project that was published, and now as future steps, we are thinking, okay, what can we do with this, right? And this has two sides. So first of all, there are a lot of adversarial applications of this, but security research sometimes is about adversarial applications of things. And so because first of all, you can steal the model, and this in itself is something developers might not want, that someone is able to steal the model. Or you can try to modify the model to inject a vector, where vector can do many things, but for instance, one thing you might want to do is to maliciously modify the model such that it misclassifies some specific things. Now you might say, okay, I want to change this model so that a stop sign is not recognized as a stop sign anymore. Maybe only under some specific conditions that only the attacker knows, right? And so, of course, you cannot do it if you need to modify some complicated code like this, but you can do it much more easily if you have the high-level representation of the neural network. Okay, and so the idea here would be that once you have a modified machine learning model, then you can recompile it and then injecting it into the device. But on the other hand, there are also defensive applications, because of course, now that you can lift the binary, you can extract the neural network representation, you can harden it, or you can patch it to maybe fix some problems, or retrain it partially to improve the classification. So again, we go into the area of patching existing code, and so another application that we are exploring for the future is to get the binary implemented neural network, extract the original neural network, fix it, and then deploy it again in the device. And so this is the name of a few projects in this area. And okay, so the last topic I want to talk about is a few projects we have been working on in collaboration with Google. So Google has been pretty kind with us and gifting us some money to do some research. And so one thing we look into is again about software updates and software patching. We look into how IoT devices get updates. And why is this an Android project? It's an Android project because a lot of IoT devices, of course, you control them with an Android app. It's called a companion app. And in a lot of cases, this companion app also takes care of sending the update to the device. So the device doesn't get the update directly, but this update mechanism is mediated by an Android app. And so, of course, the device is supposed to check that the update is actually coming from the official vendor. But in a lot of times, these checks are not done properly. And so this, of course, can lead to two possible scenarios. One is that an attacker is able to send a malicious software update, and then the malicious code can do anything the attacker wants. Or you send the malicious updates, the device understands that this update is malicious, but the malicious updates at that point has been kind of written on the device already, and so the device gets, basically you break the device. You cannot use it anymore because the device recognizes that the software updates has been compromised, but then it doesn't know what to do, and there is no way to fix it. And we found this kind of surprisingly common. We found this scenario surprisingly common. And potentially another malicious scenarios is that you could send an update that was officially released by the vendor, but it's an older version. It's an older version that maybe it contains a vulnerability. And so you can send an older update and then exploit the vulnerability into it. So these three scenarios should be avoided, of course. And so we investigated how apps mediate updates and the libraries that apps use to perform these updates. And we found that a lot of these libraries and the corresponding IoT devices controlled by these libraries do not implement updates correctly. And so we kind of developed a semi-automated procedure to do this, so that we could do kind of a large-scale analysis on a good amount of different IoT devices that we bought from Amazon and other sellers, and then we analyzed a lot of Android apps to find how they connect with the device to send updates. And just to maybe mention one case, we found, for instance, that there is an SDK, so a library released by Wemo that basically the way in which it works is that the Android app sends a message to an MQTT server that is kind of a middleware server. This message contains a command that is sent to the IoT device, telling to the IoT device to update the code. But this command also contains the URL where the IoT device should go and fetch the update. But we found that if you change this URL, the IoT device will go to the wrong place and try to get the update from there. And then the IoT device is able to, if you send a modified update, the IoT device will detect that the update has been maliciously modified. But in doing this, the original code running on the device gets overwritten, and so then the device gets bricked. You cannot use it anymore. And so you need to, I don't know, if you have warranty, maybe you can get it back, but otherwise it's gone. And so we found this used by a few IoT devices, but the interesting part here is that once we contacted the company, they told us, yes, we know about this, but this software has been deprecated maybe, I don't know, 4 years ago, so we don't really care anymore. And this answer maybe is legitimate, but the problem is that a lot of top seller devices on Amazon, they were still using this old software a few months ago when we checked. So on one hand, it's reasonable that this software is not maintained anymore, or there are newer and safer versions of it. But then the vendors using this software, they should have either stopped using it or stopped selling those devices or update those devices. So again, we go into the problem that updating is hard and vendors don't do it often enough. Okay, so the last project, still in collaboration with Google, is about still the interaction between Android apps, but in this case, the interaction between Android apps and the apps running on your smartwatch. So you have a smartphone, you have a smartwatch, and there are a lot of apps that you have a version of them on the watch and a version of them on the phone, and they communicate with each other, they exchange data. And the interesting part here is that, at least in Android, the apps on the phone and the apps on the watch, they use, on the phone and on the watch, you have two separate and parallel permission models. So on the phone, you can say, I don't want this app to be able to access my location. Or you can say, I want this app to be able to access my location. And on the watch, again, you can say, I want this app to be able to access my location, or I don't want it. But the interaction between these two permission models is not that straightforward, and it's actually pretty confusing, even for us that we studied it for a long time. So we cannot imagine how confusing it is, might be for users using this system. And in fact, we showcases, we tested the fact that you can have a scenario in which maybe you don't give a permission to the phone app to access the location, and you give this permission to the smartwatch app to access the location, but then the two applications, they talk with each other. And so regardless of the fact that you didn't give the permission of one of the two apps, the other app is is going to share the location with the app on the smartphone. So there is kind of a cross-device information sharing that might not be what the user would like to, and might not be what the user understands that is happening. So to evaluate these like more formally, we perform user studies in which we ask to the users, what do you think is happening here? Which data do you think this app can access in this scenario? And of course, users are quite confused and are not very aware about the fact that the smartwatch apps and the smartphones apps, they can share sensitive data. And kind of similarly, we also found the case in which sometimes the watch can tell you, okay, now you need to go on the phone and approve a permission on the phone. And the watch can show you something like that, like can show you something, the app needs camera access, and then you go on the phone and you approve it on the phone. But on the phone, actually, we found that if you show a request on the phone from a different permission, like in this case, files, the user wouldn't really not notice this discrepancy in most of the cases, because we are all lazy, we just click accept, 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 or allow, so we don't check here, we don't read, we don't check carefully, so we just allow everything, and so the user might not be aware that the user might be maliciously lured into allowing an unwanted permission on the phone. And so again, we did a user study in which we simulated these scenarios, and then the participants of the study actually, most of them were not understanding what was happening and exactly which permissions they were giving to the app on the phone. Okay, so I guess my colleague can present some other project.
Thank you. Okay, hi everyone. So I'm super happy to be here. So my name is Berkay. Quickly, I will give an overview of my research based on the domains that we apply our knowledge. So the first one is robotic vehicles. Okay? So basically, you can consider as drones or any kind of ground mobile robots as well. So this is an architecture, how it works. Okay? So we have user commands, environmental factors, and some configuration parameters. Then these inputs go to the control software of the drone, and then the drone starts operating, right? It has a yaw, pitch, and roll. And then what happens is, from the sensors, you collect data. For instance, what's your height, right? And then the control program then makes a decision and changes the actuators, in this case. Okay, so this is how it works. So drones are becoming extremely important for delivery, surveillance, or even we see, like in mission critical systems as well. So what we have done is, everybody was doing fuzzing. So fuzzing is a software testing approach. You send a set of inputs, then try to kind of trigger some bugs, okay? And then you have a feedback. You know which inputs to mutate, and then again you send some inputs to cause like some memory corruption, or maybe like buffer overflows. So what we said is, okay, we are not trying to fight traditional software bugs, but we are trying to focus on logic bugs. So let me tell you what logic bug is. So if you think a logic bug, it's kind of like a semantic bug, or it's a kind of requirement that the drone needs to satisfy when operating. Okay? So in this case, for instance, what we say is, a vehicle must not deploy a parachute when the vehicle is in a flip or acro flight modes, or it's climbing. So I'm telling you this to you, and I'm giving you the control software program, and then I just say, can you please check the code to see whether this policy violated or logic bug violated or not? How are you going to do that? So this is a research problem. Okay? This is, in our research, we kind of implement tools, okay, develop techniques to address such concerns. Because each of these violations can be triggered also from an adversary. Okay, so the first part was basically we would like to find the logic bugs in the control software. So we need the policies, and then we need a kind of tool in order to find them. So we implement a kind of tool called PGFuzz over here. after we have implemented this, we have a sequence of other research, which we try to automatically patch whenever a policy violation is found, or whenever there is a logic bug, we try to patch them automatically. But one thing, if you patch a software, you need to ensure whether your patch is correct, or whether your patch prevents the bug, but it doesn't cause anything else in the software as well, right? So how are you going to verify that patch is not causing anything else? This might be depleting your battery, this might be making the drone slow, this might be like not preserving its altitude, or maybe other traditional software errors. So in the third work, what we have done is we have implemented this patch verification system. Okay. All right, so drones, lots of exciting things happening, but of course, when you learn about the drones, it's flying, you know, there's a control software, the lots of different sensors are there. We also work on autonomous vehicles. So autonomous vehicles, I would say a little bit complex because it integrates also AI components, machine learning components, okay? So when you look at, you pursue the environment, then you do some prediction, and then you do planning, and then you do control, and you give an actuation command to your brakes, steering, etc. Okay? So all of these pipelines, if you kind of zoom in, what you're gonna see is simply you need a technique to understand your environment, to predict what they're gonna do in 5 minutes, then you need to make a decision. So let me think in this way, right? We are trying to have human intelligence in the autonomous vehicles. So if I'm looking here, I need to kind of understand there are multiple people around me. It's a kind of within a bounding box, labeled with a pedestrian. Some of you are maybe moving, that's fine. I need to track you as well, so that I know where you are moving, right? And then maybe I should also predict in 30 seconds where you're gonna be if you are moving. Then I need to do a command, right? Whether to turn right, whether to preserve my speed, or whether to stop. So lots of complex components together working. Okay. Of course, if you have such a system, there will be lots of attacks as well. Okay? So most of the people attacks object detection component of the autonomous vehicles. It has a deep learning algorithm. It senses the environment, whether either through a camera or LiDAR. After this, it just detects using an object detection algorithm in order to detect what's in my environment. People put some stickers to make the stop sign, yield sign. People created objects. They just project. This is one of the most difficult attacks. They just put a pedestrian and make the car stop. Okay? People used, like some kind of light, powerful lights, in order to change the pixels in the stop sign as well. This might cause a misclassification. The stop sign might be a kind of yield sign too. Okay? Of course, the autonomous vehicles not only use camera, they use LiDAR as well, where there is a X, Y, and Z, right? The depth information. The researchers come up with some techniques to attack LiDARs as well, all right? So what we have done is, we try to develop some defense techniques, okay? So when considering these defense techniques, we just look at different objects, and we say, our goal is to prevent misclassification attacks. For instance, if you would like to make the car as a pedestrian, which is one of the objectives of an adversary, you can do that. Like how we can defend against this? What might be the solution? So we use some spatial temporal consistency. As you see here, the car and the person has different bounding box. The shape is different. And over time, this needs to be preserved. So spatial is the shape, okay? And over time, it's a kind of temporal impact. So if you just use this logic, okay, you can detect like most of the misclassification attacks. Because they put a sticker to a human, the human becomes like a car. But you don't change the bounding box like a car, right? So then I can raise an alarm. However, if attacker knows our defense technique, attackers might be adaptive, right? They're gonna change the class plus the bounding box as well. So this is called adaptive adversary. So for that reason, what we have done is we had like more context information. Like what about if we use the speed? Because the person's speed is different than the vehicle speed. Or the traffic sign doesn't have a speed, right? So maybe we can use the other objects' velocities around as well. So we collect all this information. We use a recurrent neural network. So this can be used as a detector whenever misclassification attack happens and warn the system. So that system maybe takes some recovery actions. Okay. All right, I'll quickly go over a couple of things as well, very fast. So object detection is only one part of the perception. Okay. After you detect the object, you need to track the object. So, if I give you 3 frames, for instance, okay, T1, T2, and T3, and some pedestrians, let's say there are 3 pedestrians on this. In every frame, these pedestrians are in different locations. How are you going to understand, in the first frame, there is a pedestrian, but in the second frame, which one is which? Right? Which one is which? How are you going to track that? Most of you see, take algorithms class, right? So what happens is this. You're going to use some stable matching algorithm between these frames. Okay? Stable matching algorithm, which the most popular one is the Hungarian algorithm. By looking at some properties of these objects, maybe you can use some semantic information, or maybe you can use the speed of them and try to match them with less error. Okay? So there is a huge pipeline. So if you do an attack to object detection, that doesn't mean that you can also impact the object tracking. For that reason, you need to develop new attacks. What we have done in this project, we show that object detection attacks doesn't work for object tracking, because object tracking works differently. If you would like to attack them, you need to, for instance, a person is moving right, you might try, adversary can try to make it move left, or vice versa. We call them moving and move out attacks. Okay? And we demonstrate community that these attacks can be very easily done in real world. So we need to have some defense techniques. Okay, so this is kind of like our solution, like how we are constructing the attack. But most interestingly, all right, in order to do these attacks in the physical world, you need a projector. The attacker needs to project something, right? Some type of noise, or needs to go to the traffic sign and put a kind of a patch or something, right? So we said we would like to attack autonomous vehicle with an adversarial vehicle. So what I'm going to do is, the black one here is the attacker car. I will find such maneuvers that I will make the yellow autonomous car crash. But when I'm doing my maneuvers, I will have a low liability. Meaning, I will not directly crash. I will obey the traffic rules and then make that crash. As you see here, the black car is the adversarial car, doing some maneuvers around the yellow car, and the yellow car crashes there. Okay? So, I'm going to stop here. I think, Dongyan, you can continue, or I can show a couple of videos. If you have time.
Why don't you show it now, then I will just need like a
Okay, so I want to show you a couple of examples here, okay? So for instance, this might be a very simple maneuver, you know, a little bit. But it allows the vehicle crash the red vehicle. Why? Because the vehicle sees both vehicles as a single bounding box. And it sees like a moving, because the bounding boxes are merged, right? And then because the car, black one, moves, you just crash. Okay? So let's look at one more example, and I guess we are done. So by the way, we are doing these experiments at Purdue campus. See, we have projected some noise to the traffic. Okay, let's watch this again. Some signs over there. Do you see how the tracker from vehicle goes away, moves out? Now we applied noise to the Did you see that? Do you see, this is the noise that we are applying through our projector. And now what's going to happen is, you were tracking the vehicle, suddenly the record goes. So it means that I can just speed up and move on. Alright. Okay, if you are interested, later on I can show you more videos, but I now just leave to Dongyan to finish up.
So this is just a kind of a small sample of the projects that we do at Purdue. So we actually have other application scenarios, dealing with other things like manufacturing, transportation, sports engineering, and all kinds of things. So so this is actually a scenario. This is a story I would like to tell you. So this is a what they call the virtual cycling competition, where you have a server, maybe run by the International Olympic Committee. They actually feed data about the terrain, the route, for these cyclists, so that they can actually virtually, these competitors are located in different geographic locations, in US, Canada, Mexico, Europe, all over the world. But they are getting the data feed, all of them get the same data feed from, the virtual, let's say the virtual Olympic Games. And then they actually, the data gets translated into their, the digital control signals that control the site, the bikes, right, that the competitor is riding. So like 4 years ago, there was actually a attack, they nicknamed the attack the e-doping, meaning that you don't actually have to do the doping, because doping is harmful to one's health. What they did is to hack into the communication between the bike and that edge device, so that this competitor's performance can be exaggerated, right? Gaining some unfair advantage over the other competitors. So we're actually working with the IOC, International Olympic Committee, and also the the UCI. It's a French name, Universal Cycling Federation or something, to actually address the security and privacy and fairness issue, in this big end-to-end architecture. So this is actually yet another typical computer architecture that spans the cloud, where the competition server runs, the edge, where you see that monitor that collects, a local competition data, and the device, the IoT device, which is the bike, right? And then how do you actually secure the entire end-to-end data communication, computing, reporting, computation? So that's actually a very interesting and kind of, out of the box, projects, right? They said, who said that cybersecurity cannot be fun? So we do, try to have some fun while working on these very serious projects. In fact, this architecture is actually, to be very honest, not too far away from some of the more, critical applications, related to national security and defense. Cloud, edge, IoT, right? That's actually the very common architecture that, that exists in a wide variety of domains. So the good news is that you can actually leverage a lot of the solutions that you develop for one scenario, and then you can actually adapt and apply it to many other scenarios. So we are actually adopting a solution, the anti-cheating solution here, to a secure manufacturing application. So I think that's actually quite amazing. So I'm actually going to stop here. So, I'm hoping that, we kind of give you just a quick sample of what we do. And yeah, so we very much love to, involve, some of you in these efforts. So we at Purdue, we do offer, summer undergraduate student research opportunity. We actually involve students, undergraduate students, not only from Purdue, but also across the country to participate in some of the research projects. And, I particularly love to work with Zach, because, we've been talking about, collaborating. So I think, these plus many others would be some concrete platforms where we can actually do some cool things together. So with that, I will maybe, there are still a couple of minutes, maybe we could, the three of us would like to get to answer any of your questions, if you have any.
So let's say I'm a student that's interested in doing some of this stuff. What should I do to get involved? How do I get started?
I guess we do need to have a contact information slide, which I don't have. My apologies. Yeah, send us an email. So maybe either contact Zach and Sid. They can actually kind of relay your interest to us. Or if you can Google, so Google Purdue PurSec, and you can get our contact information. And so do feel free to contact us. And even just stop by maybe anytime. We're just 85 miles apart. Took us 2 hours to come here though, but and yeah, so we also have our annual symposium, and also we have our cybersecurity training camp, that where we actually welcome students not only from Purdue but also from all universities across Indiana. So yeah, so there are multiple ways to engage, and so we very much love to hear from you.
What
Yes.
would the training camp be?
So the next one will happen in March 2024, where we actually, a team from Rose-Hulman participated last year. So we have, day one, going through some, training, learning about how, cyber forensics, cyber incidents response. And day two, we're gonna give you a challenge, like a mock-up scenario, and multiple teams compete to investigate the same incident and see which team come up with the most comprehensive and most accurate analysis. Yeah. And there will be prizes. Yes, sir.
So the part about decompiling neural networks from stuff, what kind of neural networks would you find in binaries? I would imagine a lot of the really cool stuff would be cloud-based.
Exactly. I also initially, for sure, a lot of things is cloud-based, but I think we found cases, for instance, for face recognition, or for I think also if you have something like the Alexa device, I think recognizing the Alexa word just for that part is done in the device. Or I think we found also some speech recognition or some object tracking for cameras that they need to kind of recognize if something is really moving or is not moving. So
any type, they call it tiny ML.
Yes.
Right?
Yeah, these are not huge network like ChatGPT or something like that. These are like smaller network, and of course, on the device there is only the inference part. All the training is done somewhere else, but it's not that uncommon actually. And I think there are 3 or 4 compilers that have been designed specifically to do this. And of course, these embedded systems sometimes they have a specific hardware to support implementing this network in a low power accelerated way.
Good question. Yeah.
Thank you very much. So now we'll move to the part I sent in the email for those of you interested in talking more about research. These folks are going to stick around. So those of you interested in talking about research, CTFs, and all these collaboration opportunities, feel free to please stay.
Yes. Yeah. Yes, in regards to sorry. You good?
Yeah.
All right. Yep. We're giving presentation.
Yes.